do some practice exercise on what we learned from decimals. First of all, let's do some simple computations to simplify a mixture of decimals and fractions. Okay, so this fraction is 0.2 cubed divided by 0.02 squared. To simplify this, I would suggest to convert the decimal number into rounded number into integers first, and then do the exponents and fractions. So how to convert that? Remember that 0.2 equivalent to 2 times 10 to the power of minus 1, and 0.02 equivalent to 2 times 10 to the power of minus 2, and this is squared. So that, because this is multiplication, I can then distribute the exponents to each term. So it's 2 power of 3 times, remember what we learned from exponents, 10 to power of a with power of b is 10 to power of a times b. Right, so this minus 1 times 3 is minus 3, divided by, similarly, 2 squared times 10 to minus 4, right? 2 times 2 is 4. And then you can either start the cancellation, or you can further rewrite the fraction with a negative power, right? Divided by 2 squared means multiplying by 2 to the power of minus 2. This equivalent to multiplying 10 to the power of 4, right? By changing the sign of the exponent. And then grouping the number with the same base, 2, 3 minus 2 times 10 minus 3 plus 4. That is 2 to the power of 1, 10 to the power of 1. So it's 20, right? So this is how you can simplify the mixture of the fraction and decimal. Okay, next question. Convert fraction to decimal. So 39 over 20, which a simplified way is 20 seems too large to be divided by, but if I divide 10 on both sides, I will have 3.9 over 2. Now, this because I want to convert to a decimal anyway, so I don't mind to have a decimal on my numerator first, and then 3.9 divided by 2, you can just use the long division, it will be 1.95. Right, this is how you convert that. Or a more complicated one, 4 over 21. So 4 over 21, first of all, there's no common factor to further cancel out or to further simplify this fraction. This is also a fraction that already less than 1. So the only way you can do is to do the long division to find the answer. You need to divide 4 by 21. We'll start from 1, 21, 1, 9, 0, and it will keep going. I'll leave this detailed calculation for you. So eventually this will be, like, remember in the last class we checked the decimal form of 1 over 7, and 21 contains a factor of 7. So you can imagine that it's going to be a very long repeating decimal. So it in fact is 0.190476 repeating. So it has 6 digits of repeating. Okay, next one. Convert decimal to fraction now. So this one is 0.08 with 8 repeating. So basically, what we had in the previous example, if you only have one digit repeating, you probably just need to multiply by 10. If you have 2 digits repeating, looks like you need to multiply by 100. So how many digits repeating? You're multiplying by that many of the power of 10. So this one, I will let x equal to 0.08, 8 repeating, so that 10x will be 0.8 repeating. So what happens if I use 10x subtract x? This equivalent to have 0.888 to subtract 0.088 repeating. Right, so all the 8s are repeating, so give you all the zeros, but the first decimal place 8 minus 0 is 8, this is 0, and 10x minus x is 9x. So 9x is 0.8. Solving from here, x is 0.8 over 9. Converting them from decimal to integer first, I will have 8 over 90. And then I can further simplify by dividing the common factor. Obviously, number 2 is a common factor. Do I have more common factors? 2 is not, 3 is not. So that's all. So that's the simplest form. So this means this decimal 0.08 with 8 repeating can be converted into a fraction of 4 over 45. Right, so let's see another example. 0.321 with number 2 and 1 repeating. As I just said, this time I have 2 digits repeating. So it looks like I need to multiply by power of 2. So again, first of all, I let x to be 0.321 with 1 repeating, and I'm multiplying 100 because there's 2 digits repeating. This is 32, right? 100 means I need to move the stop 2 steps. So it's 32, 1, 2, 1, 2, 1, 2, keep going. Now, how about the subtraction? 100x minus x is 32.121212, and x is 0.32121221. Keep going, right? Then the subtraction starts from these digits to give you all repeating zeros to the end. But before this digit, you need to do the calculation by yourself. So 1 minus 3, 11 minus 3 is 8. You need to borrow 1 number, so 32 becomes 31. So that's it. On the left-hand side, this is 99x. So I have 99x equals 31.8. So my x is 318 over 990. So I'm not only just dividing 99 over there, I'm also converting decimal to be an integer by multiplying another 10. And then you can simplify this by further canceling out at least 2 is a common factor. So I have 159 over 495. It's not divisible by 3. This is 3. This is not divisible, is it? 53 over 1, 6, 5. Is there any further factors? I think there's no further factors. You can try if you can find more common factors, but I couldn't. So eventually this repeating decimal can be converted to a fraction of 53 over 165. Okay, let's see the next example. How many positive integers that less than 100 have reciprocals with terminating decimal representation? Right, so terminal decimal is equivalent to finite decimal, and the reciprocal of integers are, for example, 1/2, 1/3, 1/4, keep going. And remember what we learned in the last example of the previous class, that we present a list of the decimal form of 1/2, 1/3 until 1/10, and we conclude from there that as long as your denominator's only prime factor must be 2 or 5 or 2 and 5. This is the only scenario that can make the reciprocal of integer to be a finite decimal or terminating decimal. All right, for example, 1/2 equals 0.5. It's a finite decimal because denominator 2 contains only prime factor of 2, but 1/3 is not. 1/3 is a repeating infinite decimal, right? Because the denominator 3 does not contain prime factor of 2 and 5, and it contains a prime factor of 3 other than 2 and 5. So this question then can be converted to looking for integer numbers less than 100 that only contains prime factor of 2 or 5 or both 2 and 5. So find the integer that less than 100 contains only the prime factor of 2 or 5 or both 2 and 5. So this means I need the number of multiple of 2, right? Because multiple of 2 only contains prime factor of 2. And I also want number that are multiple of 5, right? 5 is also a number contains prime of 5. But if I'm only listing these two scenarios, for example, the first scenario will give you 2, 4, 8, 16, 32, 64, right? And then the next would exceed in 100. Let's see what would be the next. 128, that is greater than 100. Or multiple of 5 will be, sorry, to be precisely speaking, that's power of 2 and power of 5. Right? 525. Next is 125, which is exceeding 100 already. And then the number of power of 2, both 2 and 5. So combination of 2 and 5 would be a little bit complicated because I could have 2 times 5, which is 10. Have 2 squared times 5, because for single 2 and single 5 I already have them. So I only need to care about the combination of 2 and 5. and the minimum combination is 1, 2, and 1, 5. That gives you 10. Now I can fix the 5 to increase the power of 2 first. So this is 4 times 5. That is 20. 8 times 5, 40. Right? I don't need to write the left hand side. It's just keep multiplying by 5 by 2. I would have 80. And then the next will be 160. That is exceeding 100. So I stop here by increasing power of 2. I can still increasing power of 5. 2 times 25 is 50. Next would be 2 times 125. 250, that's obviously greater than 100. So we're reaching the 100 limits in all three scenarios, and we can start counting how many such combinations. I have 6 numbers in scenario number 1. I have 2 counts here. I have 1, 2, 3, 4, 5 counts in scenario number 3. So altogether I have 13 such integer that is less than 100, and the reciprocals are terminating decimal, finite decimal. Okay, let's see one last example. Okay, the first part of the example, to compute 7 over 10 plus 7 over 100 plus 7 over 1000, and keep going with the same pattern. So the first one, the pattern is we have the same numerator 1 by 1, and then the denominator is increased 10 times 1 by 1. So this one I can, because the denominator is 100, I can easily convert each fraction into a decimal number. So I'll have 0.7 plus 0.07 plus 0.007. Each time your denominator increasing by 10 times, I have one more zero after the decimal, or the decimal point moving one step to the left. So I will have 0.7 repeating. And that's it for the first question. So I can rewrite or I can compute these fractions, rewrite them into decimal. Now the second, if I have 6 over 10 plus 3 over 100 plus 6 over 1000 plus 3 over 10,000, and keep going. Now this one, the pattern being changed a little bit, because the denominator is still increasing by 10 times 1 by 1, but the numerator keep repeating between 6 and 3 and 6 and 3. So this means I need to think of how to put them together, right? Because I would have 0.6 plus 0.03 and plus 0.006 and 0.30 with 3. We keep going, right? So if I'm writing all the 6 together, imagine there's small digits. I will have 0.6, 06, and 06. Keep going, right? There's a 0 in between because 6 are not continuous. It's every second term. Similarly to 3, 3 is also every second term. So the first term is 0.03. I will have a 0 in between, and 3, the 0 and 3, and keep going. So this would be 0.60 with 60 repeating, and 0.03 with 03 repeating. So now I can put them together. the same as the simple addition. So I'll have 0.63 repeating. So it's a 2 digits repeating. Okay, so the last one to compute 1/3 plus 1/9 plus 1/27 plus 1/81, and keep going. Now this one, unlike the previous examples, though those are the previous examples, you're always dividing by a power of 10, so you can easily convert each single fraction into a decimal number and then put them together, right? This one, you don't have a denominator that is power of 10. Denominator, so the pattern is actually the denominator is a 3 and multiple of 3, and keep multiplying 3 one by one. So what would be the pattern? Like, first of all, they are not easily converted into decimals. Like, even if you have to convert them from this first one, I remember the second one is 0.1 repeating, but what is 1/27? It's going to be a complicated repeating number and with no pattern. Like, actually, you can try, I would encourage you to try to find out what is 1/27 and what is 1/81 to see if you can find any pattern. So at least I could not find a pattern from this way. So this means that we need to think about a different approach, right? This one can borrow the same idea. Like, remember how when we converting the repeating decimal into fractions, we sometimes don't solve the unknown question directly. We use the indirect way to assign a term that equal to a known combination and then try to transform the term. So for example, I can let the sum s to be 1/3 as the original sequence, right? And then because I observe that each denominator is increased by 3 times, so 3 times s is 3 times this sequence. And then if I'm putting this in, 3 times 1/3 is 1. The next term is 1/3. The next term is 1/9. The next term is 1/27. So it's switching for one term, but the repeating pattern is the same because these are all multiple of 3s. So the repeating pattern is the same. That means the rest of the repeating component is also equal to our original assumption of s. Now I have an equation of 3s equal to 1 plus s. I'm moving this back. I have 2s equal to 1, and I can solve x to be 1/2. So indeed, this infinite sum, this sequence is just equal to 1/2 by solving by this method. Okay, so that's all for the practice of decimals.